This is Math 139, and we're looking at section 4.11, talking about solving equations that contain radicals. So, the basic overview here, we are going to isolate the radical on one side of the equation. If there are two, we'll get them on opposite sides, but we don't want any more than one radical on each side. Apply inverse operations to get x by itself. So, for example, squaring a square root or cubing a cube root. Once we've done that, we should get an equation that we know how to solve. Once we've solved, however, number 3 is important here. It is important to check our solutions. It's sometimes possible to get what are called extraneous solutions. That is, you can do everything right, but you can still get an answer out of the solution process that doesn't satisfy the original equation. We'll see, I think, at least one example of that as we go through here. All right, so we'll start with number 1. The square root of x minus 3 is equal to 5. The radical is already all by itself on the left-hand side. So all I'm going to do is apply the inverse. Inverse of a square root would be to square. And of course, if I do something on one side, I have to do it also on the other side of the equation. The square root is the inverse of a square, so they do and undo, meaning all I'm going to get over here is x minus 3. And on the right-hand side, I'd have 25. When I add the 3 over, x equals 28. And that should be all set. I probably should have done this before I circled that answer, but let me just make mention. It's perfectly fine to check in your calculator. You could probably do this one mentally as well. But notice that if I did take the square root of 28 minus 3 on my calculator, it does give me the 5. So I know I'm good to go there. All right, in number 2, this time we have a cubed root. And the other thing I want to be careful with here is the fact that that cubed root, that radical, is not by itself on the left-hand side of the equation. Got this plus 2. So I'm going to subtract the 2 before I do anything else. Isolate the radical is what that step is called. All right, now that the radical is isolated, I'm going to say that the inverse of the cubed root is the third power, or cubing function. So I'll do that to both sides. Again, those are inverses, so I'm left with just the x. And 3 cubed is 27. We'll just check this one in our heads. The cube root of 27 would be 3, and 3 plus 2 is indeed 5. So that's a legitimate solution. All right, let's try a few more. In number 3, once again, I want to start by isolating my radical. So I will add the 4. And then I'm also going to divide by the 5. I will admit that I can get by without that. In fact, we might see one later where I'll choose not to do it. But since the 5 goes into the 15 easily, I'm going to go ahead and do it. It's going to make things a little easier. All right, the square root of x plus 1 is all by itself on the left-hand side. It's isolated. So squaring a square root is the inverse function. Let the inverses act, and I end up with just x plus 1 equals 9. And so x equals 8. Just for convenience, maybe I'll go ahead and check this one on the calculator. If I take 5 times the square root of 8 plus 1 and subtract 4, I do indeed get 11, as expected. All right, number 4. Once again, my radical's not isolated. I would need to subtract the 8 from both sides. So I have the 4th root of 3x minus 1 equals negative 3. And the inverse of the 4th root would be the 4th power. Let the inverses act on one another, leaving me just the 3x minus 1 on the left. And negative 3 to the fourth power, you either know it in your head or you can always put it in the calculator. Don't forget if you put it in the calculator that those parentheses are really important, right? Negative 3 to the fourth power is 81. I'll add the 1 over and divide by the 3. Now, 3 doesn't go into 82 evenly, so I'm just going to go ahead and leave my final answer in its exact form, the fraction form, 82 thirds. And then I want to check this. So let's see here. I would like to take 8 plus the fourth root of 3 times 82 thirds minus 1. And notice I get 11, not 5, like I expected. So this is an example of an extraneous root. I didn't do anything wrong in the process, but I still got an answer that does not work. So I'm going to have to say this time, nope, didn't work out, and there is no solution. I would mention that you may have picked up on the fact that that was going to happen early on, and if you did, you were definitely sharp today. But notice way back up here, when I had the fourth root of something being negative, that was actually a signal right there that it wasn't going to work. Even roots, square roots, fourth roots, sixth roots, always come out positive. Only the odd roots can come out negative. So that was actually a little hint way back there that this was not going to work. All right, we have a couple more examples to try. In example 5, there are two radicals, and we mentioned a little bit at the beginning here of this video that when there are two radicals, we want to get them on opposite sides. So I'm just going to take the one that's negative and I'm going to add it over to the right. There we go. All right, it's impossible to completely isolate both radicals. That 3 has to be on one side or the other. And I'd rather not create a fraction, so I'm just going to leave it on the side that it's on right now. All right, these are square roots, so the inverse function would be to square. I'll square both sides. And here's where you have to be a little bit careful. Notice that when you're squaring, this time you have two factors, and you'll have to square both of them. 3 squared is going to give me 9, and then squaring the square root gives me just x minus 4. 9 multiplies that whole thing, so I did put parentheses in, so I don't forget to distribute the next step. The other side's a little bit more straightforward. Squaring the square root just gives me 3x plus 5. All right, we will distribute, so I have 9x minus 36 equals 3x plus 5. And let's subtract the 3x and add the 36. So I have 6x equals 41. And again, it's not going to come out evenly, so I'm just going to give the exact answer. X equals 41/6. All right, let's check. 3 times the square root of 41/6 minus 4. Subtract the square root of 3 times 41/6 plus 5. And it did give me 0, which is exactly what I needed, so this one works. All right, in example 6, once again, my first task is to get that radical by itself, so I'm going to subtract the 1, move it over to the right-hand side. And to get rid of the square root, I use the inverse, which would be to square. Left-hand side straightforward, squaring the square root just gives me the 2x plus 5. But do be careful on the right. Notice this is subtraction, right? Not multiplication. I can't just try to distribute or apply that square. I actually have to multiply the 2x minus 1 times itself. I'm going to write that out just as a reminder. It's going to be the FOIL process. So I'd have 4x squared minus 2x minus another 2x plus 1. Or 4x squared minus 4x plus 1. This is quadratic, so I'm going to get it equal to 0. 0 would equal 4x squared minus 6x minus 4. All right, so let's see. I have to solve that quadratic. Let me see. We can definitely factor out a 2. 2x squared minus 3x minus 2. And are we going to be able to come up with a sum of negative 3 and a product of negative 4? Looks like that one is going to work. Negative 4 and positive 1 would do that. So I have my 2x squared. Instead of the negative 3x, I'll write it as negative 4x plus 1x. And then that minus 2. And then I'll factor by grouping. 2x times x minus 2 plus, all I can factor out there is really just a 1, so 1 times x minus 2. Factoring out the common binomial of x minus 2, and then I've got the 2x plus 1. All right, if x minus 2 is 0, then x equals 2. And if 2x plus 1 is 0, then x would be negative 1/2. Let's try them. The square root of 2 times 2 plus 5. Oops. Plus 1 is 4. And of course over here 2 times 2 would also be 4. So that looks like it works just fine. What about the negative 1/2? Square root of 2 times negative 1/2 plus 5 plus 1 is 3. But 2 times negative 1/2 would be negative 1, not 3. So this one does not work. It's an extraneous solution. Although it's not true that this happens every time, I will say that it's very common when you have a quadratic and you get 2 solutions for one of them to work and the other one to not work. You always have to check them both because it's possible that neither of them work. It's possible that they both work. It happens. But it's really, really common that one will and one won't. All right. One last example. At number 7, we have the square root of x is equal to the square root of 3x minus 2. Notice that it's impossible to isolate both radical terms. No matter what, you're always going to have either a subtract 2 on this side, or else I'd have to bring it over and make it an add 2 on the other side. It is possible to solve equations like this by hand, by squaring both sides, but you're going to end up with a FOIL process on one side. And actually, it ends up you have to do it twice. Although it's possible, I'm actually not going to require that you do problems like this by hand in this particular class. Instead, when we have 2 radicals like that, where it's impossible to isolate, we'll go ahead and just use graphing technology to solve. So I'm going to go ahead and I'm going to use Desmos to graph both of these, and then we'll just look and see what the intersection point is. So just as a reminder, we'll graph y equals the square root of x, and we'll also graph y equals the square root of 3x minus 2. And we'll look for the intersection. So I'm going to swap us over to Desmos here. All right, there we are. And we'll put in our first one, which was just y equals the square root of x. Let's see, I need to pull that up a little bit. There we go. And then our second one, which was the square root of 3x minus 2. And we can see right here, there's our intersection point. And I only need the x value, right? My equation only had x's in it, so I'm only solving for x. And to 3 decimal places, that's 7.464. All right, so x is approximately 7.464. And I will say when you use this method, you're pretty sure that this is going to work. You've actually seen it on a graph. It's not something that's going to have an extraneous solution, although it doesn't hurt to plug the values back in here to double check. The check is a little more optional when you've used a graphical method. All right, that brings us to the end of section 4.11.